now that we know what eigenvalues and eigenvectors are, let's actually calculate some. So let's find all the eigenvalues and associated eigenvectors for this matrix. So remember to find the eigenvalues. So eval is my abbreviation for eigenvalue. So we can just solve the characteristic equation for this matrix, which again is the determinant of lambda I minus A. Right, set this equal to 0. So first let's write down what this determinant is. So we're going to take the determinant of, so let's see, lambda I is just this matrix, 0's off the diagonal and lambda's on the diagonal, minus A, so 11 minus 18, 6 minus 10, okay, equals 0. So we're going to take the determinant of that, we need to take the determinant of lambda minus 11, positive 18, minus 6, and lambda plus 10. And then we're going to set that equal to 0. So this determinant is, let's see, lambda minus 11 times lambda plus 10 plus 6 times 18, so that's 60 plus 48, 48, 108. Okay. To solve this, we're going to have to multiply this all out. So now we're just solving a polynomial equation. This one happens to be quadratic since it's degree 2. So let's see, lambda squared minus lambda minus 110 plus 108. I think I multiplied that out right. So lambda squared minus lambda minus 2 equals 0. So this factors, because I cooked this example up special so that it would. So this is lambda minus 2 times lambda plus 1. And so we get two eigenvalues, 2 and minus 1. Notice that since our matrix was 2 by 2, right, since our matrix was 2 by 2, the characteristic polynomial is degree 2, so we're going to have at most 2 eigenvalues. Right? If you have a degree 2 polynomial, you can have at most 2 solutions, maybe just one solution if there's a repeated solution, and maybe no real solutions. But for this example, we got two real eigenvalues. All right, so now we have the eigenvalues. Let's find the corresponding eigenvectors. In other words, the eigenspace that corresponds to each one of these eigenvalues. Remember, each eigenvalue is going to have its own eigenspace, so you have to sort of do these separately, unfortunately. So for lambda equals 2, the way that I like to do this is write down A minus lambda I. So this is, just because I find it easier to keep track of the minus signs this way. So lambda is 2, and our original matrix is way up here. So, right, we're doing A minus lambda I, so we just need to subtract lambda from the diagonal elements. So off diagonal, it's still minus 18 and 6. And then on the diagonal, we're subtracting lambda, so 9 and 12. 9 and 12, minus 12, minus 12. Okay. Now, when you're finding the eigenvectors associated to an eigenvalue, you're actually also checking that your eigenvalues are correct, because we know ahead of time that if lambda really is an eigenvalue, this matrix should be singular. Right? Or another way to say singular is it shouldn't be invertible, or its rows shouldn't be linearly independent. Or when we row reduce this matrix, we shouldn't get the identity, right? Those are all the same, all different ways of saying the same thing. So So let's row reduce this and see if we do get the identity. We know ahead of time that we shouldn't, right? If we actually are dealing with an eigenvalue, this should not row reduce to the identity. So let's see, we can divide the first row by 3, I guess, and divide the second row by 2. We get 3 minus 6, and then here we get 3 minus 6. Oh, I should have divided by 3 again. Let's see. Well, yeah, so row reducing, you can see that this second row is going to get zeroed out. So row 2 minus row 1, that's going to zero out the second row. And then we can divide the first row by 3 again. We're going to get 1 and minus 2. Okay, so this means that the null space is, so in general we need to write down the general solution to this equals 0 and then parameterize it and get some basis vectors for the null space, but since there's only one equation here that isn't 0, we can just look at it and sort of understand what a solution is. So it looks like 2, 1. Right? I'm just writing down some vector that when I multiply it by this matrix, I get 0. And 2, 1 certainly fits the bill. So the eigenspace associated to the eigenvalue 2 is the span of the vector 2, 1. Okay. This means that if we take our original matrix and multiply it by 2, 1, we ought to get twice 2, 1. So I won't actually work through that arithmetic, but right, now that we have an eigenvector eigenvalue pair, that's what it's saying. Right? So in this direction, in the direction 2, 1, the matrix A is acting like multiplication by 2. Okay, well that was just the first eigenvalue. Remember there's another eigenvalue, minus 1. So let's find the eigenspace associated to the eigenvalue minus 1. Okay, so off the diagonal it's minus 18 and 6. And then on the diagonal it's minus 9 and, oh, I forget. Sorry, eigenvalue is minus 1, so I need to subtract minus 1, so I need to add 1, so 12. Okay. All right, so this is A minus lambda I. Now we need to solve the homogeneous equation associated to this matrix, right? Set it equal to 0, the 0 vector, and solve, right? So we can row reduce this. Let's see, divide the second row by 3, I guess, and the first row by 6. So first row we're going to get 1 minus 3, and second row we're going to get, I'm sorry, 2 minus 3. Second row we're going to get 2 minus 3. Okay, and then we can do row 2 minus row 1. 2 minus 3, 0, 0, right? So because we have a square matrix and we know ahead of time it had better be singular, that means when you do this row reduction, there had better be a row of zeros. If there isn't a row of zeros after you're done row reducing, you know you made a mistake, right? If that happens, this isn't really an eigenvalue. But we are ending up with a row of zeros, so we really do have an eigenvalue. And we can write down the null space of this matrix. Right? So again, in general, we would have to write down the solution to, general solution to this matrix equals 0. We'd have to parameterize the solution, come up with basis vectors. But because it's going to be spanned by just a single vector, we can just kind of think of a vector that when multiplied by this matrix would give you 0, and minus 3, 2 does the job. Right? if you take minus 3, 2 times this, actually I guess we need a plus 3, don't we? Yes, plus 3, 2 times this matrix would give you 0. So here's the eigenspace associated to the eigenvalue minus 1. Right? So we had two eigenvalues, 2 and minus 1, and they each have an eigenspace that goes along with it, 2, 1 and 3, 2. Notice that these eigens, first of all, the eigenspace associated to an eigenvalue isn't just the 0 vector, right? That should never be the case. If that's what you find, you made a mistake. And also, for these different eigenvalues, the corresponding eigenvectors can't be parallel, right? They can't be multiples of each other, and that makes perfect sense because, right, if you have an eigenvector, multiplying it by the matrix should be the eigenvalue times the vector. But if you had one vector that was in two different eigenspaces, which lambda would show up here? That wouldn't really make sense. So those are just a couple things to check to make sure that your calculations of eigenvalues and eigenvectors make sense.